Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrenner, and today we're talking about circuits. We will define DC power, and we will talk about power consumed and power supplied. When we talk about DC power, we can talk about the power consumed by a resistor. And resistors will never generate power, so they will always have a positive power consumed. And we define the relationship for power as P is equal to I times V, the current times the voltage. And I remind people to just say PIV, just like we said VER for the Ohm's law. It's just a quick mnemonic to help you out. So when we talk about the power consumed by a resistor, I'll put PC just to make it clear that it's power consumed. We use the voltage across the resistor and the current through the resistor. We're following the passive sign convention. The current, as defined, enters the positive node of the voltage. If we wanted to have the current going the other direction for some reason, maybe somebody else defined it for you, then you would just have a negative sign. So we have P consumed is equal to I times V. So for the resistor, that's going to be I of the resistor times the V of the resistor, as I've shown in the diagram. We can then include Ohm's law and plug in from V is equal to IR. We know that V is equal to I times R, which would give us the current squared times the resistance. Again, the current squared will be positive and the resistance is positive, so the power consumed will definitely be positive. We can also use the relationship that with Ohm's law that IR is equal to VR over R. So we plug that in, multiply by VR, and we get the power consumed is equal to VR squared over R. Again, VR squared will be positive, so VR squared over R will also be positive. Just a reminder that the power consumed by a resistor is positive. And the units will be watts. Volts times amps gives you watts. Let's consider an example. I've drawn a circuit here with a 10 volt source and a 5 ohm resistor. I've defined VR across the 5 ohm resistor as shown, and the current going into the positive side. Okay, so we know that PIV, P is equal to I times V. We don't know the current through the resistor, so first we would need to calculate that. But we do know that V is, in our case, VR. VR is equal to 10 volts because the positive node here is the same as the positive node here, and the negative is a negative. So they're same direction, same voltage. Remember, these wires have no voltage drop. They're considered ideal wires. Now we can use Ohm's law to tell us that IR is equal to VR divided by R. So that will be 10 volts divided by 5 ohms, which will give us 2 amps. From that, we can calculate power. P is equal to IR times VR, which will give me 2 amps times 10 volts, which will give me 20 watts. Now, we could have done this simply using the definition of the other definitions of power. So we could have used P is equal to V squared over R, which would have been 10 volts squared over 5 ohms, which gives us 100 over 5, which is 20 watts. Okay, same answer. We can also use the equation I squared R. And I was 2, so 2 amps squared times 5 ohms. 2 amps squared times 5 ohms gives us 4 times 5, again, 20 watts. Now, most people are able to compute the number, but what gives people problems is the direction. So is it power consumed? Well, anytime a resistor has power, it doesn't generate power. Resistors only consume power. So that will be your quick check. But what you should also remember is that power consumed is always defined as the current going into the positive voltage and out of the negative voltage. So if I ask you a different question, what if I ask you what is the power generated by that resistor? You would say minus 20 watts. Let's work a quick problem. Suppose you're given a circuit, and I'm going to use an 8 volts and 3 ohms. And I want to know what is the power consumed by the 3 ohm resistor. Again, what we need to know is the voltage across that resistor. I'm going to call it VR, and the current going into that resistor, IR. We know that VR is equal to 8 volts, and IR will be equal to VR divided by 3, which gives me 8 divided by 3, and leave it, and that will be amps. I find that it's usually easier to leave it as fractions at this point, so we'll just leave it at 8/3 amps. Of course, that is 2 2/3 amps. Okay, but if we leave it as 8/3 amps, we'll have less numerical problems, and it's actually a lot quicker and easier. So now we can say that the power consumed by the resistor will be equal to VR times IR, which will be equal to 8 volts times 8/3 amps, which will give me 64/3 watts. And at this point, we can give the value as a number, and it will be 21 1/3 watts, which is 21.3333, however long you want to go, and that would be the power consumed. Now, what is the power supplied by that resistor? Well, we know that resistors always consume power, so the power supplied will be the opposite of the power consumed. So that means P supplied by the resistor will be equal to minus 21.3333 watts. This is a good time, I think, to talk about significant figures. Sometimes when I have students from other majors where significant figures are emphasized for various reasons, it gives them a bit of a confusion. And what I would like to talk about is this is not an actual measured value. If we were doing measured values, then using significant figures would make sense. Instead, we are analyzing an ideal circuit. So this value is exact to however many digits, and this value is exact to however many digits. So for my students, I usually just tell them to keep as much precision as they can as they work the problem. And in your answer, give enough significant figures. Err on the side of more, not less, but 4 or 5 digits past the decimal is typically fine. Now let's consider a different question. Here's the same circuit with an 8 volt power supply and a 3 ohm resistor. And this time we're going to ask the question, what is the power supplied by the voltage source? So again, I recommend that you would actually compute the power consumed by the voltage source. So P consumed will be defined by the voltage across, I'm going to call it VS for voltage source, and the current going into. So consumed, the power consumed by the voltage source, and I don't normally write this all out, but just to keep it clear, will be equal to I going into the source times the voltage across the source. Again, we're using the same passive sign convention where we define the current going into the plus side. I'm sorry, if you always compute the power consumed whether it's a voltage source or current source, which we haven't talked about, or a resistance, and then you can answer the question that's asked: what's supplied, what's consumed. It will be easier for you. So the power consumed by the voltage source is equal to IS times VS. We know that the voltage source, of course, is VS is equal to 8 volts. Now the current going into this source is the same as the current going up through that resistor. So we can figure out what IS is using Ohm's law. So IS, which of course is this, same current, I'll just write it there again for your benefit, will be equal to the voltage across the resistor divided by the resistance, 3 ohms. And the voltage across the resistor now is equal to the negative of the voltage of the source. Again, we're defining VR where the current goes into that positive resistance. And since I'm defining it, I have the choice of how to do it. So we know that VR is going to be minus 8 volts, the opposite of the power source, divided by 3. So IS will be minus 8/3 amps. And we'll just leave it as a current, and we will just leave it as a fraction. So now we know what IS is. IS going this way is the same as this IS going here. So we can talk about the power consumed by the voltage source. So I'll call it PCVS for just as a reminder, will be equal to IS, which is minus 8/3 amps. And of course, the voltage across the voltage source is 8 volts. And that will be equal to minus 64/3 watts. Okay, which is equal to minus 21.3333 watts. So what you notice at this point is that the power consumed is actually a negative value. That means that actually the power supplied, which is the question I asked, power supplied by the voltage source, will be equal to the opposite of the power consumed, so that'll be 21.3333-ish for however long you need to go, watts. Now, one thing I want you to notice that in this simple circuit, the power supplied by that voltage source is 21 1/3 watts, and the power consumed by this resistor is 21 1/3 watts. This is just conservation of power, and it makes sense because the wires are ideal. There's no power loss in the wires, no power consumed by the wires, no voltage drop across them. So we have to have power conservation, and we end up with the voltage source and the current. The voltage source supplies the same amount of power that is consumed by the resistor. In more complicated circuits, this is also true, but it's harder to see directly. So we've done 2 problems calculating the power consumed and the power supplied. Problem 1 was computing the power consumed by a resistor, and problem 2 was computing the power supplied by the voltage source. And we saw that in this simple circuit, we do have conservation of power. Thank you very much. Good luck.